First-order logic is a formal system used in mathematics, philosophy, linguistics, and computer science. It is also known as first-order predicate calculus, the lower predicate calculus, quantification theory, and predicate logic. First-order logic is distinguished from propositional logic by its use of quantified variables. A theory about some topic is usually first-order logic together with a specified domain of discourse over which the quantified variables range, finitely many functions which map from that domain into it, finitely many predicates defined on that domain, and a recursive set of axioms which are believed to hold for those things. Sometimes theory is understood in a more formal sense, which is just a set of sentences in first-order logic. The adjective first-order distinguishes first-order logic from higher-order logic in which there are predicates having predicates or functions as arguments, or in which one or both of predicate quantifiers or function quantifiers are permitted. In first-order theories, predicates are often associated with sets. In interpreted higher-order theories, predicates may be interpreted as sets of sets. There are many deductive systems for first-order logic that are sound and complete. Although the logical consequence relation is only semi-decidable, much progress has been made in automated theorem proving in first-order logic. First-order logic also satisfies several metalogical theorems that make it amenable to analysis in proof theory, such as the La paragraph-in-Heimer-Euroscolum theorem and the compactness theorem. First-order logic is the standard for the formalization of mathematics into axioms and is studied in the foundations of mathematics. Mathematical theories, such as number theory and set theory, have been formalized into first-order axiom schemata such as Peano arithmetic and Zamilowa-Euro-Frankel set theory respectively. No first-order theory, however, has the strength to describe fully and categorically structures with an infinite domain, such as the natural numbers or the real line. Categorical axiom systems for these structures can be obtained in stronger logic such as second-order logic. For a history of first-order logic and how it came to dominate formal logic, see Joseph copyright for Era Cubed S. Introduction. While propositional logic deals with simple declarative propositions, first-order logic additionally covers predicates and quantification. A predicate takes an entity or entities in the domain of discourse as input and outputs either true or false. Consider the two sentences Socrates is a philosopher, and Plato is a philosopher. In propositional logic, these sentences are viewed as being unrelated and are denoted, for example, by P and Q. However, the predicate is a philosopher occurs in both sentences which have a common structure of A as a philosopher. The variable A is instantiated as Socrates in the first sentence and is instantiated as Plato in the second sentence. The use of predicates, such as is a philosopher in this example, distinguishes first-order logic from propositional logic. Predicates can be compared. Consider, for example, the first-order formula if A is a philosopher, then A is a scholar. This formula is a conditional statement with A as a philosopher as hypothesis and A as a scholar as conclusion. The truth of this formula depends on which object is denoted by A, and on the interpretations of the predicates is a philosopher, and is a scholar. Variables can be quantified over. The variable A in the previous formula can be quantified over, for instance, in the first-order sentence for every A, if A is a philosopher, then A is a scholar. The universal quantifier for every in this sentence expresses the idea that the claim if A is a philosopher, then A is a scholar holds for all choices of A. The negation of the sentence for every A, if A is a philosopher, then A is a scholar is logically equivalent to the sentence there exists as such that A is a philosopher and A is not a scholar. The existential quantifier there exists expresses the idea that the claim A is a philosopher and A is not a scholar holds for some choice of A. The predicates is a philosopher, and is a scholar each take a single variable. Predicates can take several variables. In the first-order sentence Socrates is the teacher of Plato, the predicate is the teacher of takes two variables. To interpret a first-order formula, one specifies what each predicate means and the entities that can instantiate the predicated variables. These entities form the domain of discourse or universe, which is usually required to be a non-empty set. Given that the interpretation with the domain of discourse as consisting of all human beings and the predicate is a philosopher understood as have written the Republic, the sentence there exists is such that A is a philosopher is seen as being true, as witnessed by Plato. Syntax. There are two key parts of first-order logic. The syntax determines which collections of symbols are legal expressions in first-order logic, while the semantics determine the meanings behind these expressions. Alphabet. Unlike natural languages, such as English, the language of first-order logic is completely formal, so that it can be mechanically determined whether a given expression is legal. There are two key types of legal expressions: terms, which intuitively represent objects, and formulas, which intuitively express predicates that can be true or false. The terms and formulas of first-order logic are strings of symbols which together form the alphabet of the language. As with all formal languages, the nature of the symbols themselves is outside the scope of formal logic. They are often regarded simply as letters and punctuation symbols. It is common to divide the symbols of the alphabet into logical symbols, which always have the same meaning, and non-logical symbols, whose meaning varies by interpretation. For example, the logical symbol always represents and. It is never interpreted as or. On the other hand, a non-logical predicate symbol such as phil, X, could be interpreted to mean X is a philosopher, X is a man named Philip, or any other unary predicate, depending on the interpretation at hand. Logical symbols. There are several logical symbols in the alphabet, which vary by author but usually include the quantifier symbols a euro and a florin, the logical connectives, a section for conjunction, a for disjunction, a for implication, a for biconditional, a for negation. Occasionally other logical connective symbols are included. Some authors use CPQ instead of a, and EPQ instead of a, especially in contexts where A is used for other purposes. Moreover, the horseshoe ash florin may replace A. The triple bar permel may replace A. A tilde, NP, or FPQ, may replace A. Or APQ may replace A. And, KPQ, or the middle dot, A, may replace a section, especially if these symbols are not available for technical reasons. Parentheses, brackets, and other punctuation symbols. The choice of such symbols varies depending on context. An infinite set of variables, often denoted by lowercase letters at the end of the alphabet X, Y, Z, a euro. Subscripts are often used to distinguish variables, XO, X1, X2, a euro. An equality symbol equals. See the section on equality below. It should be noted that not all of these symbols are required a euro. Only one of the quantifiers, negation and conjunction, variables, brackets and equality suffice. There are numerous minor variations that may define additional logical symbols, sometimes the truth constants T, VPQ, or ash currency, for true, and F, OPQ, or ash yen, for false are included. Without any such logical operators of valence zero, these two constants can only be expressed using quantifiers. Sometimes additional logical connectives are included, such as the Sheffer stroke, DPQ, and exclusive OR, JPQ. Non-logical symbols. The non-logical symbols represent predicates, functions and constants on the domain of discourse. It used to be standard practice to use a fixed, infinite set of non-logical symbols for all purposes. A more recent practice is to use different non-logical symbols according to the application one has in mind. Therefore it has become necessary to name the set of all non-logical symbols used in a particular application. This choice is made via a signature. The traditional approach is to have only one, infinite, set of non-logical symbols for all applications. Consequently, under the traditional approach there is only one language of first-order logic. This approach is still common, especially in philosophically oriented books. For every integer n per mil beta 0 there is a collection of nr, or n-place, predicate symbols. Because they represent relations between n elements, they are also called relation symbols. For each arity n we have an infinite supply of them, Pn0, Pn1, Pn2, Pn3, a euro. For every integer now a permil beta 0 there are infinitely many n of function symbols, fno, fn1, fn2, fn3, a euro. In contemporary mathematical logic, the signature varies by application. Typical signatures in mathematics are 1, a, or just a, for groups, or 0, 1, plus, a, for ordered fields. There are no restrictions on the number of non-logical symbols. The signature can be empty, finite, or infinite, even uncountable. Uncountable signatures occur for example in modern proofs of the La paragraph in Heimskillum theorem. In this approach, every non-logical symbol is of one of the following types. A predicate symbol with some valence greater than or equal to 0. These are often denoted by uppercase letters P, Q, R. Relations of valence 0 can be identified with propositional variables. For example, P, which can stand for any statement. For example, P, X, is a predicate variable of valence 1. One possible interpretation is X is a man. Q, X, Y, is a predicate variable of valence 2. Possible interpretations include X is greater than Y, and X is the father of Y. A function symbol, with some valence greater than or equal to 0. These are often denoted by lowercase letters f, g, h. Examples, f, x, may be interpreted as for the father of x. In arithmetic, it may stand for x. In set theory, it may stand for the power set of x. In arithmetic, g, x, y, may stand for x plus y. In set theory, it may stand for the union of x and y. Function symbols of valence 0 are called constant symbols, and are often denoted by lowercase letters at the beginning of the alphabet A, B, C. The symbol A may stand for Socrates. In arithmetic, it may stand for 0. In set theory, such a constant may stand for the empty set. The traditional approach can be recovered in the modern approach by simply specifying the custom signature to consist of the traditional sequences of non-logical symbols. Formation rules. The formation rules define the terms and formulas of first-order logic. When terms and formulas are represented as strings of symbols, these rules can be used to write a formal grammar for terms and formulas. These rules are generally context-free, except that the set of symbols may be allowed to be infinite and there may be many start symbols, for example the variables in the case of terms. Terms. The set of terms is inductively defined by the following rules. Variables. Any variable is a term. Functions. Any expression f, t1, tn, of n arguments is a term. In particular, symbols denoting individual constants are 0 are function symbols, and are thus terms. Only expressions which can be obtained by finitely many applications of rules 1 and 2 are terms. For example, no expression involving a predicate symbol is a term. Formulas. The set of formulas is inductively defined by the following rules. Predicate symbols. If P is an n a predicate symbol and T1, Tn are terms, then P, T1, Tn, is a formula. Equality. If the equality symbol is considered part of logic, and T1 and T2 are terms, then T1 equals T2 is a formula. Negation. If I is a formula, then I is a formula. Binary connectives. If I and I are formulas, then is a formula. Similar rules apply to other binary logical connectives. Quantifiers. If I is a formula and x is a variable, then and are formulas. Only expressions which can be obtained by finitely many applications of rules 1 a 5 are formulas. The formulas obtained from the first two rules are said to be atomic formulas. For example, is a formula, if f is a unary function symbol, p a unary predicate symbol, and q a ternary predicate symbol. On the other hand, is not a formula, although it is a string of symbols from the alphabet. The role of the parentheses in the definition is to ensure that any formula can only be obtained in one way by following the inductive definition. This property is known as unique readability of formulas. There are many conventions for where parentheses are used in formulas. For example, Some authors use colons or full stops instead of parentheses, or change the places in which parentheses are inserted. Each author's particular definition must be accompanied by a proof of unique readability. This definition of a formula does not support defining an if-then-else function int, C, A, B, where C is a condition expressed as a formula, that would return A if C is true, and B if it is false. This is because both predicates and functions can only accept terms as parameters, but the first parameter is a formula. Some languages built on first-order logic, such as SMT-lib 2.0, add this. Notational conventions. For convenience, conventions have been developed about the precedence of the logical operators, to avoid the need to write parentheses in some cases. These rules are similar to the order of operations in arithmetic. A common convention is evaluated first, and are evaluated next, quantifiers are evaluated next, is evaluated last. Moreover, extra punctuation not required by the definition may be inserted to make formulas easier to read. Thus the formula might be written as. In some fields, it is common to use infix notation for binary relations and functions, instead of the prefix notation defined above. For example, in arithmetic, one typically writes 2 plus 2 equals 4 instead of equals, plus, 2, 2, 4. It is common to regard formulas in infix notation as abbreviations for the corresponding formulas in prefix notation. The definitions above use infix notation for binary connectives such as. A less common convention is Polish notation, in which one writes, and so on in front of their arguments rather than between them. This convention allows all punctuation symbols to be discarded. Polish notation is compact and elegant, but rarely used in practice because it is hard for humans to read it. In Polish notation, the formula becomes a euro za euro ya pfx apxkixts. Free and bound variables. In a formula, a variable may occur free or bound. Intuitively, a variable is free in a formula if it is not quantified. In variable x is free while y is bound. The free and bound variables of a formula are defined inductively as follows. Atomic formulas. If I is an atomic formula, then x is free in I if and only if x occurs in I. Moreover, there are no bound variables in any atomic formula. Negation. X is free in I if and only if x is free in I. X is bound in I if and only if x is bound in I. Binary connectives. X is free in if and only if x is free in either I or I. X is bound in if and only if x is bound in either I or I. The same rule applies to any other binary connective in place of. Quantifiers. X is free in y if and only if x is free in I and x is a different symbol from y. Also, x is bound in y if and only if x is y or x is bound in I. The same rule holds within place of. For example, in XYQ, X, F, X, Z, X and Y are bound variables, Z is a free variable, and W is neither because it does not occur in the formula. Free and bound variables of a formula need not be disjoint sets. X is both free and bound in. Freeness and boundness can be also specialized to specific occurrences of variables in a formula. For example, in the first occurrence of X is free while the second is bound. In other words, the X in is free while the in is bound. A formula in first-order logic with no free variables is called a first-order sentence. These are the formulas that will have well-defined truth values under an interpretation. For example, whether a formula such as fill, X, is true must depend on what X represents. But the sentence will be either true or false in a given interpretation. Examples, abelian groups. In mathematics, the language of ordered abelian groups has one constant symbol 0, one unary function symbol a, one binary function symbol plus, and one binary relation symbol a per mole currency. Then, the expressions plus, x, y, and plus, x, plus, y, a, z are terms. These are usually written as x plus y and x plus y a z. The expressions plus, x, y, equals 0 and a per mole currency, plus, x plus y, a, z plus x, y are atomic formulas. These are usually written as x plus y equals 0 and x plus y a z a permil x plus y. The expression is a formula, which is usually written as loving relation. There are 10 different formulas with 8 different meanings that use the loving relation Lxy and the quantifiers a euro and a florin. The logical matrices represent the formulas for the case that there are 5 individuals that can love and be loved. Except for the sentences 9 and 10, they are examples. For example, the matrix representing sentence 5 stands for B loves himself. The matrix representing sentences 7 and 8 stands for C loves B. It's important and instructive to distinguish sentence 1 and 3, in both cases everyone is loved. But in the first case everyone is loved by someone, in the second case everyone is loved by same person. Some sentences imply each other a euro, for example, if 3 is true also 1 is true, but not vice versa. Semantics, an interpretation of a first-order language, assigns a denotation to all non-logical constants in that language. It also determines a domain of discourse that specifies the range of the quantifiers. The result is that each term is assigned an object that it represents, and each sentence is assigned a truth value. In this way, an interpretation provides semantic meaning to the terms and formulas of the language. The study of the interpretations of formal languages is called formal semantics. What follows is a description of the standard or Tarskian semantics for first-order logic. The domain of discourse D is a non-empty set of objects of some kind. Intuitively, a first-order formula is a statement about these objects. For example, states the existence of an object X such that the predicate P is true where referred to it. The domain of discourse is the set of considered objects. For example, one can take to be the set of integer numbers. The interpretation of a function symbol is a function. For example, if the domain of discourse consists of integers, a function symbol f of arity 2 can be interpreted as the function that gives the sum of its arguments. In other words, the symbol f is associated with a function I, f, which, in this interpretation, is addition. The interpretation of a constant symbol is a function from the one-element set DO to D, which can be simply identified with an object in D. For example, an interpretation may assign the value to the constant symbol. The interpretation of an n, a predicate symbol, is a set of n tuples of elements of the domain of discourse. This means that, given an interpretation, a predicate symbol, and n elements of the domain of discourse, one can tell whether the predicate is true of those elements according to the given interpretation. For example, an interpretation I, P, of a binary predicate symbol P may be the set of pairs of integers such that the first one is less than the second. According to this interpretation, the predicate P would be true if its first argument is less than the second. First-order structures. The most common way of specifying an interpretation is to specify a structure. The structure consists of a non-empty set D that forms the domain of discourse and an interpretation I of the non-logical terms of the signature. This interpretation is itself a function. Each function symbol f of arity n is assigned a function I, f, from 2. In particular, each constant symbol of the signature is assigned an individual in the domain of discourse. Each predicate symbol P of arity n is assigned a relation I, P, over or, equivalently, a function from 2. Thus each predicate symbol is interpreted by a Boolean-valued function on D. Evaluation of truth values. A formula evaluates to true or false given in interpretation, and a variable assignment I1/4 that associates an element of the domain of discourse with each variable. The reason that a variable assignment is required is to give meanings to formulas with free variables, such as the truth value of this formula changes depending on whether x and y denote the same individual. First, the variable assignment I1/4 can be extended to all terms of the language, with the result that each term maps to a single element of the domain of discourse. The following rules are used to make this assignment: variables. Each variable x evaluates to I1/4, x, functions. Given terms that have been evaluated to elements of the domain of discourse, and a n a function symbol f, the term evaluates to. Next, each formula is assigned a truth value. The inductive definition used to make this assignment is called the T-schema. Atomic formulas. A formula is associated the value true or false depending on whether, where are the evaluation of the terms and is the interpretation of, which by assumption is a subset of. Atomic formulas. A formula is assigned true if and evaluate to the same object of the domain of discourse. Logical connectives. A formula in the form, etc. is evaluated according to the truth table for the connective in question, as in propositional logic. Existential quantifiers. A formula is true according to M and if there exists an evaluation of the variables that only differs from regarding the evaluation of X and such that I is true according to the interpretation M and the variable assignment. This formal definition captures the idea that is true if and only if there is a way to choose a value for X such that I, X, is satisfied. Universal quantifiers. A formula is true according to M and if I, X, is true for every pair composed by the interpretation M and some variable assignment that differs from only on the value of X. This captures the idea that is true if every possible choice of a value for X causes I, X, to be true. If a formula does not contain free variables, and so is a sentence, then the initial variable assignment does not affect its truth value. In other words, a sentence is true according to M and if and only if it is true according to M and every other variable assignment. There is a second common approach to defining truth values that does not rely on variable assignment functions. Instead, given an interpretation M, one first adds to the signature a collection of constant symbols, one for each element of the domain of discourse in M. Say that for each D in the domain the constant symbol CD is fixed. The interpretation is extended so that each new constant symbol is assigned to its corresponding element of the domain. One now defines truth for quantified formulas syntactically, as follows: existential quantifiers. A formula is true according to M if there is some D in the domain of discourse such that holds. Here is the result of substituting CD for every free occurrence of X in I. Universal quantifiers. A formula is true according to M if, for every D in the domain of discourse, is true according to M. This alternate approach gives exactly the same truth values to all sentences as the approach via variable assignments. Validity, satisfiability, and logical consequence. If a sentence I evaluates to true under a given interpretation M, one says that M satisfies I. This is denoted. A sentence is satisfiable if there is some interpretation under which it is true. Satisfiability of formulas with free variables is more complicated, because an interpretation on its own does not determine the truth value of such a formula. The most common convention is that a formula with free variables is said to be satisfied by an interpretation if the formula remains true regardless which individuals from the domain of discourse are assigned to its free variables. This has the same effect as saying that a formula is satisfied if and only if its universal closure is satisfied. A formula is logically valid if it is true in every interpretation. These formulas play a role similar to tautologies in propositional logic. A formula is a logical consequence of a formula if every interpretation that makes I true also makes I true. In this case one says that I is logically implied by I. Algebraizations, an alternate approach to the semantics of first-order logic, proceeds via abstract algebra. This approach generalizes the Linebaum-Tarski algebras of propositional logic. There are three ways of eliminating quantified variables from first-order logic that do not involve replacing quantifiers with other variable-binding term operators: cylindric algebra, by Alfred Tarski and his co-workers; polyadic algebra, by Paul Helmholtz; predicate functor logic, mainly due to Willard Quine. These algebras are all lattices that properly extend the two-element Boolean algebra. Tarski and Given showed that the fragment of first-order logic that has no atomic sentence lying in the scope of more than three quantifiers has the same expressive power as relation algebra. This fragment is of great interest because it suffices for Peano arithmetic and most axiomatic set theory, including the canonical ZFC. They also prove that first-order logic with a primitive ordered pair is equivalent to a relation algebra with two ordered pair projection functions. First-order theories, models, and elementary classes. A first-order theory of a particular signature is a set of axioms, which are sentences consisting of symbols from that signature. The set of axioms is often finite or recursively enumerable, in which case the theory is called effective. Some authors require theories to also include all logical consequences of the axioms. The axioms are considered to hold within the theory, and from them other sentences that hold within the theory can be derived. A first-order structure that satisfies all sentences in a given theory is said to be a model of the theory. An elementary class is the set of all structures satisfying a particular theory. These classes are a main subject of study in model theory. Many theories have an intended interpretation, a certain model that is kept in mind when studying the theory. For example, the intended interpretation of Peano arithmetic consists of the usual natural numbers with their usual operations. However, the La paragraph in Heimer-Euroscolum theorem shows that most first-order theories will also have other, non-standard models. A theory is consistent if it is not possible to prove a contradiction from the axioms of the theory. A theory is complete if, for every formula in its signature, either that formula or its negation is a logical consequence of the axioms of the theory. Gar paragraph Dell's incompleteness theorem shows that effective first-order theories that include a sufficient portion of the theory of the natural numbers can never be both consistent and complete. For more information on this subject, see List of first-order theories and theory, empty domains. The definition above requires that the domain of discourse of any interpretation must be a non-empty set. There are settings, such as inclusive logic, where empty domains are permitted. Moreover, if a class of algebraic structures includes an empty structure, that class can only be an elementary class in first-order logic if empty domains are permitted or the empty structure is removed from the class. There are several difficulties with empty domains. However, many common rules of inference are only valid when the domain of discourse is required to be non-empty. One example is the rule stating that implies when x is not a free variable in I. This rule, which is used to put formulas into pre-next normal form, is sound in non-empty domains, but unsound if the empty domain is permitted. The definition of truth in an interpretation that uses a variable assignment function cannot work with empty domains, because there are no variable assignment functions whose range is empty. This truth definition requires that one must select a variable assignment function before truth values for even atomic formulas can be defined. Then the truth value of a sentence is defined to be its truth value under any variable assignment, and it is proved that this truth value does not depend on which assignment is chosen. This technique does not work if there are no assignment functions at all. It must be changed to accommodate empty domains. Thus, when the empty domain is permitted, it must often be treated as a special case. Most authors, however, simply exclude the empty domain by definition. Deductive systems. A deductive system is used to demonstrate, on a purely syntactic basis, that one formula is a logical consequence of another formula. There are many such systems for first-order logic, including Hilbert-style deductive systems, natural deduction, the sequent calculus, the tableaux method, and resolution. These share the common property that a deduction is a finite syntactic object. The format of this object, and the way it is constructed, vary widely. These finite deductions themselves are often called derivations in proof theory. They are also often called proofs, but are completely formalized unlike natural language mathematical proofs. A deductive system is sound if any formula that can be derived in the system is logically valid. Conversely, a deductive system is complete if every logically valid formula is derivable. All of the systems discussed in this article are both sound and complete. They also share the property that it is possible to effectively verify that a purportedly valid deduction is actually a deduction. Such deduction systems are called effective. A key property of deductive systems is that they are purely syntactic, so that derivations can be verified without considering any interpretation. Thus a sound argument is correct in every possible interpretation of the language, regardless whether that interpretation is about mathematics, economics, or some other area. In general, logical consequence in first-order logic is only semi-decidable. If a sentence A logically implies a sentence B, then this can be discovered. However, if A does not logically imply B, this does not mean that A logically implies the negation of B. There is no effective procedure that, given formulas A and B, always correctly decides whether A logically implies B. Rules of inference. A rule of inference states that, given a particular formula with a certain property as a hypothesis, another specific formula can be derived as a conclusion. The rule is sound if it preserves validity in the sense that whenever any interpretation satisfies the hypothesis, that interpretation also satisfies the conclusion. For example, one common rule of inference is the rule of substitution. If T is a term and I is a formula possibly containing the variable x, then I, Tx, is the result of replacing all three instances of x by T in I. The substitution rule states that for any I and any term T, one can conclude I, Tx, from I provided that no free variable of T becomes bound during the substitution process. To see why the restriction on bound variables is necessary, consider the logically valid formula I given by, in the signature of arithmetic. If T is the term x plus 1, the formula I, Ty, is, which will be false in many interpretations. The problem is that the free variable x of T became bound during the substitution. The intended replacement can be obtained by renaming the bound variable x of I to something else, say z, so that the formula after substitution is, which is again logically valid. The substitution rule demonstrates several common aspects of rules of inference. It is entirely syntactical. One can tell whether it was correctly applied without appeal to any interpretation. It has limitations on when it can be applied, which must be respected to preserve the correctness of derivations. Moreover, as is often the case, these limitations are necessary because of interactions between free and bound variables that occur during syntactic manipulations of the formulas involved in the inference rule. Hilbert-style systems and natural deduction. A deduction in a Hilbert-style deductive system is a list of formulas, each of which is a logical axiom, a hypothesis that has been assumed for the derivation at hand, or follows from previous formulas via a rule of inference. The logical axioms consist of several axiom schemes of logically valid formulas. These encompass a significant amount of propositional logic. The rules of inference enable the manipulation of quantifiers. Typical Hilbert-style systems have a small number of rules of inference, along with several infinite schemes of logical axioms. It is common to have only modus ponens and universal generalization as rules of inference. Natural deduction systems resemble Hilbert-style systems in that a deduction is a finite list of formulas. However, natural deduction systems have no logical axioms. They compensate by adding additional rules of inference that can be used to manipulate the logical connectives in formulas in the proof. Sequent calculus. The sequent calculus was developed to study the properties of natural deduction systems. Instead of working with one formula at a time, it uses sequents, which are expressions of the form where A1, AN, B1, BK are formulas and the turnstile symbol is used as punctuation to separate the two halves. Intuitively, a sequent expresses the idea that implies. Tableau's method. Unlike the methods just described, the derivations in the Tableau's method are not lists of formulas. Instead, a derivation is a tree of formulas. To show that a formula A is provable, the Tableau's method attempts to demonstrate that the negation of A is unsatisfiable. The tree of the derivation has at its root. The tree branches in a way that reflects the structure of the formula. For example, to show that is unsatisfiable requires showing that C and D are each unsatisfiable. This corresponds to a branching point in the tree with parent and children C and D. Resolution. The resolution rule is a single rule of inference that, together with unification, is sound and complete for first-order logic. As with the Tableau's method, a formula is proved by showing that the negation of the formula is unsatisfiable. Resolution is commonly used in automated theorem proving. The resolution method works only with formulas that are disjunctions of atomic formulas. Arbitrary formulas must first be converted to this form through scalamization. The resolution rule states that from the hypotheses and the conclusion can be obtained. Provable identities. The following sentences can be called identities, because the main connective in each is the biconditional. Equality and its axioms. There are several different conventions for using equality in first-order logic. The most common convention, known as first-order logic with equality, includes the equality symbol as a primitive logical symbol which is always interpreted as the real equality relation between members of the domain of discourse, such that the two given members are the same member. This approach also adds certain axioms about equality to the deductive system employed. These equality axioms are, reflexivity. For each variable x, x equals x. Substitution for functions. For all variables x and y, and any function symbol f, x equals yaf. X equals f. Y. Substitution for formulas. For any variables x and y and any formula I, x, if I is obtained by replacing any number of free occurrences of x in I with y, such that these remain free occurrences of y, then, x equals ya. These are axiom schemes, each of which specifies an infinite set of axioms. The third scheme is known as Leibniz's law, the principle of substitutivity, the indiscernibility of identicals, or the replacement property. The second scheme, involving the function symbol f, is a special case of the third scheme, using the formula, x equals ya equals zaf. Y equals z. Many other properties of equality are consequences of the axioms above, for example, symmetry. If x equals y then y equals x. Transitivity. If x equals y and y equals z then x equals z. First-order logic without equality. An alternate approach considers the equality relation to be a non-logical symbol. This convention is known as first-order logic without equality. If an equality relation is included in the signature, the axioms of equality must now be added to the theories under consideration, if desired, instead of being considered rules of logic. The main difference between this method and first-order logic with equality is that an interpretation may now interpret two distinct individuals as equal. That is, the equality relation may now be interpreted by an arbitrary equivalence relation on the domain of discourse that is congruent with respect to the functions and relations of the interpretation. When this second convention is followed, the term normal model is used to refer to an interpretation where no distinct individuals A and B satisfy A equals B. In first-order logic with equality, only normal models are considered, and so there is no term for a model other than a normal model. When first-order logic without equality is studied, it is necessary to amend the statements of results such as the La paragraph in Heimer-Euroscolum theorem so that only normal models are considered. First-order logic without equality is often employed in the context of second-order arithmetic and other higher-order theories of arithmetic, where the equality relation between sets of natural numbers is usually omitted. Defining equality within a theory: if a theory has a binary formula A, x, y, which satisfies reflexivity and Leibniz's law, the theory is said to have equality, or to be a theory with equality. The theory may not have all instances of the above schemes as axioms, but rather as derivable theorems. For example, in theories with no function symbols and a finite number of relations, it is possible to define equality in terms of the relations, by defining the two terms S and T to be equal if any relation is unchanged by changing S to T in any argument. Some theories allow other ad hoc definitions of equality. In the theory of partial orders with one relation symbol a per mole currency, one could define S equals T to be an abbreviation for SA per mole currency TTA per mole currency S. In set theory with one relation, one may define S equals T to be an abbreviation for XX. This definition of equality then automatically satisfies the axioms for equality. In this case, one should replace the usual axiom of extensionality by, that is if X and Y have the same elements, then they belong to the same sets. Metalogical properties. One motivation for the use of first-order logic, rather than higher-order logic, is that first-order logic has many metalogical properties that stronger logics do not have. These results concern general properties of first-order logic itself, rather than properties of individual theories. They provide fundamental tools for the construction of models of first-order theories. Completeness and undecidability. Gar-Paragraph-Dell's completeness theorem, proved by Kurt Gar-Paragraph-Dell in 1929, establishes that there are sound, complete, effective deductive systems for first-order logic, and thus the first-order logical consequence relation is captured by finite provability. Naively, the statement that a formula I logically implies a formula I depends on every model of I. These models will in general be of arbitrarily large cardinality, and so logical consequence cannot be effectively verified by checking every model. However, it is possible to enumerate all finite derivations and search for a derivation of I from I. If I is logically implied by I, such a derivation will eventually be found. Thus first-order logical consequence is semi-decidable. It is possible to make an effective enumeration of all pairs of sentences such that I is a logical consequence of I. Unlike propositional logic, first-order logic is undecidable, provided that the language has at least one predicate of arity at least two. This means that there is no decision procedure that determines whether arbitrary formulas are logically valid. This result was established independently by Alonzo Church and Alan Turing in 1936 and 1937, respectively, giving a negative answer to the Insky-Dunks problem posed by David Hilbert in 1928. Their proofs demonstrate a connection between the unsolvability of the decision problem for first-order logic and the unsolvability of the halting problem. There are systems weaker than full first-order logic for which the logical consequence relation is decidable. These include propositional logic and monadic predicate logic, which is first-order logic restricted to unary predicate symbols and no function symbols. Other logics with no function symbols which are decidable are the guarded fragment of first-order logic, as well as two-variable logic. The Beneza-Eurosha paragraph and Finkel class of first-order formulas is also decidable. Decidable subsets of first-order logic are also studied in the framework of description logics. The Laparagraph-Inheimer-Eurosculum theorem. The Laparagraph-Inheimer-Eurosculum theorem shows that if a first-order theory of cardinality I has any infinite model, then it has models of every infinite cardinality greater than or equal to I. One of the earliest results in model theory, it implies that it is not possible to characterize countability or uncountability in a first-order language. That is, there is no first-order formula I, X, such that an arbitrary structure M satisfies I if and only if the domain of discourse of M is countable. The Laparagraph-Inheimer-Eurosculum theorem implies that infinite structures cannot be categorically axiomatized in first-order logic. For example, there is no first-order theory whose only model is the real line. Any first-order theory with an infinite model also has a model of cardinality larger than the continuum. Since the real line is infinite, any theory satisfied by the real line is also satisfied by some non-standard models. When the Laparagraph-Inheimer-Eurosculum theorem is applied to first-order set theories, the non-intuitive consequences are known as Scullum's paradox. The compactness theorem. The compactness theorem states that a set of first-order sentences has a model if and only if every finite subset of it has a model. This implies that if a formula is a logical consequence of an infinite set of first-order axioms, then it is a logical consequence of some finite number of those axioms. This theorem was proved first by Kurt Gar-Paragraph-Dell as a consequence of the completeness theorem, but many additional proofs have been obtained over time. It is a central tool in model theory, providing a fundamental method for constructing models. The compactness theorem has a limiting effect on which collections of first-order structures are elementary classes. For example, the compactness theorem implies that any theory that has arbitrarily large finite models has an infinite model. Thus the class of all finite graphs is not an elementary class. There are also more subtle limitations of first-order logic that are implied by the compactness theorem. For example, in computer science, Many situations can be modeled as a directed graph of states and connections. Validating such a system may require showing that no bad state can be reached from any good state. Thus one seeks to determine if the good and bad states are in different connected components of the graph. However, the compactness theorem can be used to show that connected graphs are not an elementary class in first-order logic, and there is no formula I, X, Y, of first-order logic, in the signature of graphs, that expresses the idea that there is a path from X to Y. Connectedness can be expressed in second-order logic, however, but not with only existential set quantifiers, as also enjoys compactness. Lindström paragraph M's theorem. Per Lindström paragraph M showed that the metalogical properties just discussed actually characterize first-order logic in the sense that no stronger logic can also have those properties. Lindström paragraph M defined a class of abstract logical systems, and a rigorous definition of the relative strength of a member of this class. He established two theorems for systems of this type: a logical system satisfying Lindström paragraph M's definition that contains first-order logic and satisfies both the Laparagraph-Inheimer-Eurosculum theorem and the compactness theorem must be equivalent to first-order logic. A logical system satisfying Lindström paragraph M's definition that has a semi-decidable logical consequence relation and satisfies the Laparagraph-Inheimer-Eurosculum theorem must be equivalent to first-order logic. Limitations: although first-order logic is sufficient for formalizing much of mathematics, and is commonly used in computer science and other fields, it has certain limitations. These include limitations on its expressiveness and limitations of the fragments of natural languages that it can describe. For instance, first-order logic is undecidable, meaning a sound, complete and terminating decision algorithm is impossible. This has led to the study of interesting decidable fragments such as C2, first-order logic with two variables and the counting quantifiers and expressiveness. The Laparagraph-Inheimer-Eurosculum theorem shows that if a first-order theory has any infinite model, then it has infinite models of every cardinality. In particular, no first-order theory with an infinite model can be categorical. Thus there is no first-order theory whose only model has the set of natural numbers as its domain, or whose only model has the set of real numbers as its domain. Many extensions of first-order logic, including infinitary logics and higher-order logics, are more expressive in the sense that they do permit categorical axiomatizations of the natural numbers or real numbers. This expressiveness comes at a metalogical cost, however, by Lindström paragraph M's theorem, the compactness theorem and the downward Laparagraph-Inheimer-Eurosculum theorem cannot hold in any logic stronger than first order. Formalizing natural languages. First-order logic is able to formalize many simple quantifier constructions in natural language, such as every person who lives in Perth lives in Australia. But there are many more complicated features of natural language that cannot be expressed in first-order logic. Any logical system which is appropriate as an instrument for the analysis of natural language needs a much richer structure than first-order predicate logic. Restrictions, extensions, and variations. There are many variations of first-order logic. Some of these are inessential in the sense that they merely change notation without affecting the semantics. Others change the expressive power more significantly, by extending the semantics through additional quantifiers or other new logical symbols. For example, infinitary logics permit formulas of infinite size, and modal logics add symbols for possibility and necessity. Restricted languages. First-order logic can be studied in languages with fewer logical symbols than were described above. Because can be expressed as, and can be expressed as either of the two quantifiers and can be dropped. Since can be expressed as and can be expressed as either or can be dropped. In other words, it is sufficient to have and, or and, as the only logical connectives. Similarly, it is sufficient to have only and as logical connectives, or to have only the Sheffer stroke or the Park arrow operator. It is possible to entirely avoid function symbols and constant symbols, rewriting them via predicate symbols in an appropriate way. For example, instead of using a constant symbol one may use a predicate, and replace every predicate such as with. A function such as will similarly be replaced by a predicate interpreted as. This change requires adding additional axioms to the theory at hand, so that interpretations of the predicate symbols used have the correct semantics. Restrictions such as these are useful as a technique to reduce the number of inference rules or axiom schemes in deductive systems, which leads to shorter proofs of metalogical results. The cost of the restrictions is that it becomes more difficult to express natural language statements in the formal system at hand, because the logical connectives used in the natural language statements must be replaced by their definitions in terms of the restricted collection of logical connectives. Similarly, derivations in the limited systems may be longer than derivations in systems that include additional connectives. There is thus a trade-off between the ease of working within the formal system and the ease of proving results about the formal system. It is also possible to restrict the arities of function symbols and predicate symbols, in sufficiently expressive theories. One can in principle dispense entirely with functions of arity greater than 2 and predicates of arity greater than 1 in theories that include a pairing function. This is a function of arity 2 that takes pairs of elements of the domain and returns an ordered pair containing them. It is also sufficient to have 2 predicate symbols of arity 2 that define projection functions from an ordered pair to its components. In either case it is necessary that the natural axioms for a pairing function and its projections are satisfied. Many sorted logic, ordinary first-order interpretations have a single domain of discourse over which all quantifiers range. Many sorted first-order logic allows variables to have different sorts, which have different domains. This is also called typed first-order logic, and the sorts called types, but it is not the same as first-order type theory. Many sorted first-order logic is often used in the study of second-order arithmetic. When there are only finitely many sorts in a theory, many sorted first-order logic can be reduced to single-sorted first-order logic. One introduces into the single-sorted theory a unary predicate symbol for each sort in the many-sorted theory, and adds an axiom saying that these unary predicates partition the domain of discourse. For example, if there are 2 sorts, one adds predicate symbols and the axiom. Then the elements satisfying are thought of as elements of the first sort, and elements satisfying as elements of the second sort. One can quantify over each sort by using the corresponding predicate symbol to limit the range of quantification. For example, to say there is an element of the first sort satisfying formula I, X, one writes. Additional quantifiers can be added to first-order logic. Sometimes it is useful to say that P, X, holds for exactly one X, which can be expressed as XP, X. This notation, called uniqueness quantification, may be taken to abbreviate a formula such as XY. First-order logic with extra quantifiers has new quantifiers QX. With meanings such as there are many X such that. Also see branching quantifiers and the plural quantifiers of George Boulos and others. Bounded quantifiers are often used in the study of set theory or arithmetic. Infinitary logics. Infinitary logic allows infinitely long sentences. For example, one may allow a conjunction or disjunction of infinitely many formulas, or quantification over infinitely many variables. Infinitely long sentences arise in areas of mathematics including topology and model theory. Infinitary logic generalizes first-order logic to allow formulas of infinite length. The most common way in which formulas can become infinite is through infinite conjunctions and disjunctions. However, it is also possible to admit generalized signatures in which function and relation symbols are allowed to have infinite arities, or in which quantifiers can bind infinitely many variables. Because an infinite formula cannot be represented by a finite string, it is necessary to choose some other representation of formulas. The usual representation in this context is a tree. Thus formulas are, essentially, identified with their parse trees, rather than with the strings being parsed. The most commonly studied infinitary logics are denoted li plus or minus I squared, where I plus or minus and I squared are each either cardinal numbers or the symbol A. In this notation, ordinary first-order logic is li per mil I per mil. In the logic li per mil, arbitrary conjunctions or disjunctions are allowed when building formulas, and there is an unlimited supply of variables. More generally, the logic that permits conjunctions or disjunctions with less than I constituents is known as Lie per-mil. For example, Lie per-mil 1 I per-mil permits countable conjunctions and disjunctions. The set of free variables in a formula of Lie per-mil can have any cardinality strictly less than I, yet only finitely many of them can be in the scope of any quantifier when a formula appears as a subformula of another. In other infinitary logics, a subformula may be in the scope of infinitely many quantifiers. For example, in Lie, a single universal or existential quantifier may bind arbitrarily many variables simultaneously. Similarly, the logic Lie permits simultaneous quantification over fewer than I variables, as well as conjunctions and disjunctions of size less than I. Non-classical and modal logics. Intuitionistic first-order logic uses intuitionistic rather than classical propositional calculus. For example, A need not be equivalent to I. First-order modal logic allows one to describe other possible worlds as well as this contingently true world which we inhabit. In some versions, the set of possible worlds varies depending on which possible world one inhabits. Modal logic has extra-modal operators with meanings which can be characterized informally as, for example, it is necessary that I, and it is possible that I. With standard first-order logic we have a single domain and each predicate is assigned one extension. With first-order modal logic we have a domain function that assigns each possible world its own domain, so that each predicate gets an extension only relative to these possible worlds. This allows us to model cases where, for example, Alex is a philosopher, but might have been a mathematician, and might not have existed at all. In the first possible world P, A, is true, in the second P, A, is false, and in the third possible world there is no A in the domain at all. First-order fuzzy logics are first-order extensions of propositional fuzzy logics rather than classical propositional calculus. Fixed-point logic. Fixed-point logic extends first-order logic by adding the closure under the least fixed points of positive operators. Higher-order logics. The characteristic feature of first-order logic is that individuals can be quantified, but not predicates. Thus, is a legal first-order formula, but is not, in most formalizations of first-order logic. Second-order logic extends first-order logic by adding the latter type of quantification. Other higher-order logics allow quantification over even higher types than second-order logic permits. These higher types include relations between relations, functions from relations to relations between relations, and other higher type objects. Thus the first in first-order logic describes the type of objects that can be quantified. Unlike first-order logic, for which only one semantics is studied, there are several possible semantics for second-order logic. The most commonly employed semantics for second-order and higher-order logic is known as full semantics. The combination of additional quantifiers and the full semantics for these quantifiers makes higher-order logic stronger than first-order logic. In particular, the logical consequence relation for second-order and higher-order logic is not semi-decidable. There is no effective deduction system for second-order logic that is sound and complete under full semantics. Second-order logic with full semantics is more expressive than first-order logic. For example, it is possible to create axioms systems in second-order logic that uniquely characterize the natural numbers and the real line. The cost of this expressiveness is that second-order and higher-order logics have fewer attractive metalogical properties than first-order logic. For example, the La paragraph in Heimer-Euroscolum theorem and compactness theorem of first-order logic become false when generalized to higher-order logics with full semantics. Automated theorem proving and formal methods. Automated theorem proving refers to the development of computer programs that search and find derivations of mathematical theorems. Finding derivations is a difficult task because the search space can be very large. An exhaustive search of every possible derivation is theoretically possible but computationally infeasible for many systems of interest in mathematics. Thus complicated heuristic functions are developed to attempt to find a derivation in less time than a blind search. The related area of automated proof verification uses computer programs to check that human-created proofs are correct. Unlike complicated automated theorem provers, verification systems may be small enough that their correctness can be checked both by hand and through automated software verification. This validation of the proof verifier is needed to give confidence that any derivation labeled as correct is actually correct. Some proof verifiers, such as Metamath, insist on having a complete derivation as input. Others, such as Mysore and Isabelle, take a well-formatted proof sketch and fill in the missing pieces by doing simple proof searches or applying known decision procedures. The resulting derivation is then verified by a small, core kernel. Many such systems are primarily intended for interactive use by human mathematicians. These are known as proof assistants. They may also use formal logics that are stronger than first-order logic, such as type theory. Because a full derivation of any non-trivial result in a first-order deductive system will be extremely long for a human to write, results are often formalized as a series of lemmas, for which derivations can be constructed separately. Automated theorem provers are also used to implement formal verification in computer science. In this setting, theorem provers are used to verify the correctness of programs and of hardware such as processors with respect to a formal specification. Because such analysis is time-consuming and thus expensive, it is usually reserved for projects in which a malfunction would have grave human or financial consequences. See also ACL2 a computational logic for applicative Common Lisp. Equiconsistency, extension by definitions, Herbrandization, higher-order logic, list of logic symbols, La paragraph-in-Heim number, pre-next normal form, relational algebra, relational model, second-order logic, Skolem normal form, Tarski's world, truth table, type, notes. References, Andrews, Peter B. An Introduction to Mathematical Logic and Type Theory, to Truth Through Proof, 2nd ed., Berlin, Kluwer Academic Publishers. Available from Springer. Avigad, Jeremy. Donnelly, Kevin. Gray, David. And Rath, Paul. A formally verified proof of the prime number theorem, ACM Transactions on Computational Logic, Volume 9 No. 1 doi, 10.1145/1297658.1297660, Barwise, John. An Introduction to First-Order Logic, in Barwise, John, ed. Handbook of Mathematical Logic. Studies in Logic and the Foundations of Mathematics. Amsterdam, NL, North Holland. ISBN A978-0-444-86388-1. Barwise, John. And Etchemendy, John. Language Proof and Logic, Stanford, California, CSLI Publications, Bokiewski, Jakubs F. Maria. A Prague copyright Sci of Mathematical Logic, Dordgt, NL, D. Reidel, translated from the French and German editions by Otto Bird, Ferreira Cube des, Jose copyright. The Road to Modern Logic an Interpretation, Bulletin of Symbolic Logic, Volume 7, Issue 4, 2001, ppA 441 484, DOI 10.2307/2687794, JSTOR, Gamut, LTF. Logic, Language, and Meaning, Volume 2, Intentional Logic and Logical Grammar, Chicago, Illinois, University of Chicago Press, ISBN 0-226-28088-8, Hilbert, David. And Ackerman, Wilhelm. Principles of Mathematical Logic, Chelsea, Hodges, Wilfred. Classical Logic I, First-Order Logic, in Goebel, Lou. The Blackwell Guide to Philosophical Logic, Blackwell, Ebbinghaus, Heinz Dieter. Flum, Jar Paragraph AG. And Thomas, Wolfgang. Mathematical Logic, Undergraduate Texts in Mathematics, Berlin, Delaware, New York, Springer Verlag, 2nd edition, ISBN 978-0-387-94258-2, Rautenberg, Wolfgang, A Concise Introduction to Mathematical Logic, New York. Springer Science Plus Business Media, doi, 10.1007/978-1-4419-1221-3, ISBN A978-1-4419-1220-6. Tarski, Alfred and Givant, Stephen. A Formalization of Set Theory Without Variables. Providence RI, American Mathematical Society. External links: Haswinkel, Michiel, ed., Predicate Calculus, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-4. Stanford Encyclopedia of Philosophy, Shapiro, Stuart. Classical Logic. Covers syntax, model theory, and metatheory for first-order logic in the natural deduction style. Magnus, P.D. Forel X, An Introduction to Formal Logic. Covers formal semantics and proof theory for first-order logic. Metamath, an ongoing online project to reconstruct mathematics as a huge first-order theory, using first-order logic and the axiomatic set theory ZFC. Principia Mathematica Modernized. Potnieks, Carl. Introduction to Mathematical Logic, Cambridge Mathematics Tripos Notes. These notes cover part of a past Cambridge Mathematics Tripos course taught to undergraduate students within their third year. The course is entitled Logic, Computation and Set Theory, and covers ordinals and cardinals, posits and Zorn's lemma, propositional logic, predicate logic, set theory and consistency issues related to ZFC and other set theories.